Good evening, good afternoon, good morning, wherever you're joining us from. I hope you're well. My name is Will Arnold. I'm the institution's head of climate action, and I will be your chair for this evening's technical talk, which is called Recreating History, the Christchurch Town Hall Reinstatement. I'm just going to go through a couple of sort of logistic things first before I introduce the topic and the speakers for tonight. As always, for those of you who've joined one of these webinars before, you'll be quite familiar with this by now, I'm sure. You can ask a question at any time using the Ask a Question box, which is quite an apt name for the box, I think you'll agree. What we're going to do is we'll collect questions as we go through the talk, and then at the end of the presentation, which will last for 45 minutes, so at the end of the presentation, I will then ask questions to the speakers. So please put them in as you think of them as we go through the evening, and we'll just save them up till the end. You can view speaker profiles underneath the slides. And just the final thing to note is that if you have any technical issues, please try turning it off and back on again first. You'll be amazed how often this works with this thing. And there's a link to test your connection underneath the slides as well. I'm not going to read this whole copyright notice out, but I do have to show this at the start of every talk. So there you go. And just before we introduce tonight, just to mention a couple of other events that are coming up in the through the rest of this year. We have a structural rehabilitation conference. That's going to be in person at HQ in London, and that will be in October. So please sign up to that if you're interested in that as a topic. And then we're holding an online Using Concrete in a Changing Environment e-conference, which is a bit sooner actually. So that was in July. And that runs for something like 3 half days in a row. So looking at everything around concrete, using it within the sort of environment that we're currently in, where people are asking us to reduce our emissions and so on and so forth. You can find links to both of those in the resources tab that sits next to the Ask a Question tab. Hopefully that was clear. So I'm just going to stop sharing now. Hopefully you can see me, and you can probably see our two presenters as well. So I've been looking quite forward to tonight's talk, and I was really pleased to be asked to chair tonight. The repair and strengthening of Christchurch Town Hall was impressive enough that it earned the project the Supreme Award for Structural Engineering at last year's Structural Awards, which is an award given to the best projects of the year. And I was one of the members of the judging panel last year, and it stood out to me from the moment I first saw the award entry. I felt that the project exemplified great structural engineering. The engineers have been tasked with repairing and strengthening Christchurch Town Hall, and this was off the back of the damage in the earthquakes of 2010 and 2011, which I'm sure tonight's speakers will go into a bit more. And saving the building probably would have been enough for some people, but we felt that the response that came from the engineering team, the response to this brief, was really exceptionally good. It required intensive coordination between structural and geotechnical teams, complex and creative analysis, and this was all to lead towards minimizing the amount of strengthening and intrusive work that was required. And this building was a local landmark, so this, it's kind of raised the bar for what the local community would expect in terms of restoration. So to be able to use engineering skills like this to save what we've got, and then to go beyond that, but actually minimize the level of intervention that we even need to make in terms of physical material use and so on, all to provide the public with a space that they can continue to enjoy into the future, for me, kind of really brought together what we believe great structural engineering is all about. So I'm really looking forward to hearing more about the project tonight, and I'm delighted to introduce our two speakers. So we have Mark Brown joining us tonight, who's Project Director with Holmes Consulting. Mark has got 16 years of experience working on large projects in New Zealand, Canada, and the west coast of the USA. And he returned back to Canada to help with the Christchurch rebuild following the earthquakes that I just mentioned. Mark's got significant experience of seismic design and construction, and enjoys the challenges of repairing, strengthening, and restoring existing buildings to their former state. Mark is joined tonight by John Hare. John is the chief exec of the Holmes Group of Companies, and he's a structural engineer who has worked in New Zealand, the UK, and the US, where he established a Holmes office in San Francisco in 2000. Since 2006, John has been based back in Christchurch, where he originally started in 1985, started practicing as a structural engineer. So we have a lot to learn from John. And in August 2019, John was awarded the CSOC President's Award for his outstanding contribution to the New Zealand structural engineering profession. So I'm sure that wherever you are sat listening to us now, you are looking forward to hearing from these two great structural engineers. So without further ado, I'm going to shut up and put myself on mute and turn my camera off and hand over to John and Mark. Thank you.
Right. Thank you very much, Will. So just while we get this up and running, I'm John. I'll be introducing the first part of this just to set some of the context and perhaps create give a bit of the background, and then I'll pass over to Mark, who's the real expert here and who's done all the hard work, I'd have to say, not me. So anyway, we'll go through a few things as a note there, history and a bit of other stuff in the background before we get on to the meat of the topic, which is obviously what we did. Starting with the history, this is a notable picture for us. This is actually taken in the original Home's office, or one of the original Home's offices, and around about the time that they were just starting to work on the town hall, quite likely. Pleased to say one of those people, actually at the bottom right, still works for us on a very occasional basis. So it's a nice piece of history for us. To really understand the significance of the building, you've got to kind of look back a wee ways in Christchurch. So top left-hand corner, Christchurch was a very traditional city. It was always known as sort of one of the most English cities in New Zealand. And so most of our architecture was very much a reflection of that. The town hall, which was designed by Morris Marnie and Miles Warren, who you can see down at the bottom right-hand corner, the architects, and Holmes, the engineers, was really, I think, one of the first examples of an architecture which was maybe not uniquely ours, but certainly New Zealand striking out on its own. And so it was a really important building in the context of New Zealand architecture. It enabled things to happen in the city, perhaps, that couldn't have happened beforehand. So it was the first really international quality performing arts building that we had in Christchurch. Happy to say that enabled you to send us Des O'Connor up there on the right as one of the earliest of the performers in there. Thank you very much. But it also enabled other things to happen. So it was an interesting period. We had the 1974 Commonwealth Games were in Christchurch, and in fact several events were held in one or other part of the town hall. So it was quite a notable building in our history. Town hall itself, we'll spend a little bit of time on this just to show you where the areas of the building are. So this, if you can see my mouse, what we call Area A there is the auditorium. It's about a 3,500 seat auditorium. And most notably, it's a world-class acoustic venue. It was really made the name of the acoustical engineer, Harold Marshall, who went on to do a lot of things internationally following this building. The right-hand side, Area C, the James Hay Theatre, is more of literally a theatre for performance. It's about 1,000 seats. It was wavering on the cusp of that as we were looking at some of the issues around smoke control and so on. In the middle between those, Area B, the foyer of these two buildings, is actually it's an interesting space in itself. It's sort of basically a box sitting on top of some columns in many respects. So it's got some space up on top, three-story structure, essentially. And then to the south, Area D, which is a restaurant on the ground floor, always used to be, and just a sort of an open space above. You can see it here on that bottom right picture. It's the part of the building which is projecting at high level. You can't really make it out, but the restaurant was underneath there. And then a little part to the side of Area D, we had a kitchen and so on, some ancillary buildings, and a much smaller space, which is added on later. So as you can see, on the top right, an early picture before the greenery grew up, very much a brutalist style modern architecture. Not very handsome to some, although I rather like it. Very much of a polarizing building, but something which became very well known around the country. Moving forward, we were very lucky with this building. We had all the original documentation still available to us. And so a little snippet you can see on the right there, that was the way they did engineering back in the 60s and 70s. So it's actually quite a remarkable piece of work. When we go through the calculations, you'll find hand resolution of matrices for some of the analysis, various other sorts of things that actually we'd be pretty pleased if we could do these days, I think. Certainly it's interesting to look at and go back to see what engineering from first principles looked like. Now we come to fast forward 2010, 2011 and what happened in Christchurch. I'll open with this. It's a very famous photograph taken by just a local resident, but this was in the immediate aftermath of the main shock, which was in February 2011. And as you can see, lots of dust, rubble, basically that's our history, a lot of our buildings falling down, lots of old brick buildings, lots of dust stirred up. It's quite a striking moment. If you look very closely there, you can see a building which is actually on a lean, a significant multi-storey building, which was crippled, I should say. A shear wall failed, not dramatically enough to bring it down, but certainly that was a pretty striking failure. We lost a total of 185 people throughout Christchurch, mostly in two modern buildings. One very modern building which collapsed, the other one dating back to the 60s. So it was, by any imagination, it was a big event. The actual, when we talk about it as an event, I should say it was many thousands of events. The main shock, the first shock was out here in the plains, which happened actually in September 2010. The city came through fairly well, although at that stage we had no idea what was waiting for us. But the main earthquake that caused the damage, the Lyttelton earthquake, you can't even see the star, but in the middle there was the one that really most affected the city. And there was widespread liquefaction all across parts of the city. There was lots of shaking damage. There was lots of rock fall. It was a very serious event, and a lot of different things happened around the city. Top left there, you can see the nature of what people were dealing with. Collapse of not shop fronts at least, collapse of the upper stories of many old masonry buildings. The bottom right there, that's a relatively new, modern, expensive home on top of a cliff. We lost about 5 meters of cliff face. And as you can see, the bottom left there, people were straggling home through the bricks and debris on the street afterwards. It was quite an event. Really, it was a miracle that we didn't lose more people. The main reason we didn't was probably because so many buildings were cordoned off following the September event. And as you can see, top right, we had an international team of people. And in fact, I think the red uniforms might be a team from Wales. So lots of people came to help in the aftermath, but it was really a very big event. Following that, of course, several things happened. So bottom left there, we had a Royal Commission to determine what had happened, looking into the buildings. I'd have to say that was quite a stressful event for many people who had to go along and talk to them, as I did. Bottom right, there was lots of trouble with insurance. This looks a bit staged. It's not. One of the major insurance companies fell over and was replaced by a government authority. And nevertheless, there was lots of arguments, and there are still arguments about some of that. And top right, of course, the usual thing that happens, the politicians move in and start making promises. And so they look like they're working together at the moment, but the mayor on the right and the two central government politicians on the left, certainly it ended up frequently in conflict. And this was the time when we were crawling all over the town hall, to bring it back to the topic, and trying to figure out if it could be saved, and furthermore, if it would be saved, because there were a lot of calls for its demolition and replacement. Setting the scene for that, this was what was known at the time as the 100-day plan. This was what the government form of CERA, the Canterbury Earthquake Recovery Agency, came up with. And most notable that there's a little spot up here, which is where the town hall sits, where even as both Warren and Marnie and Holmes were involved in the 100-day plan, we were desperately trying to fight a battle to save the town hall. There were many calls, including from central government, to have it demolished. And we spent long hours, I think, arguing the case in front of the City Council, in front of Sarah, insisting that yes, it might look like it's badly damaged, and yes, it might look like you think it needs to be demolished, but actually we can save this. Don't worry that it's a bit bent and twisted. We can do the job. Oops. Going the wrong way. Apologies for that. And so, at that point, I'll hand over to Mark, who did the job.
Thanks, John. Now, in September 2010, when the first earthquake struck out at Darfield, there was actually a refurbishment going on inside the town hall. So our people were immediately on hand to actually do a rapid assessment. And for that earthquake, there actually wasn't too much damage. And so the refurbishment continued on. Now, February 2011 was obviously a different story. The earthquake was a lot closer. The energy that was put into the city and the underlying soils was massive. It caused a whole lot of liquefaction and lateral spreading, which really damaged the building. With that, if you haven't dealt with liquefaction before, just a quick overview of what that mechanism is for the soil. So, in the soil matrix beneath the water table, the soil particles are all sort of arranged, usually in a loose form for this to occur. During the earthquake, they all get shaken around and essentially densify. And through that densification process, you get the water being squeezed out between the pores. And what that translates to in things that matter to us is that water under pressure makes its way to the surface, squeezes out, but leaves essentially liquefied, unsupported layer, and then you get the ground surface subsidence associated with it. So you get a whole lot of settlement, which our building was sitting over the top of. So when we look at what that looks like inside the town hall, there was a service tunnel that ran from one end to the other, and inside that you can sort of see with the bucket there just how deep this sand and the silt that was within this basement tunnel. And then where the cracks opened up due to the settlements and the lateral spreading, we got a lot of this sand pouring out onto the beautiful marble tiles, and a whole lot of locations all around that area. Now, the second mechanism that's important in the Christchurch Town Hall context is the lateral spreading that occurred. So when the liquefaction occurs, you have this liquefied soil, and if you have a free edge such as a river, in our case we had not only a river but also a slope down towards the river, so we have gravity and liquefied soil, and essentially getting close to the river you get really large movements, and as you get further away from the river, the movements start to dissipate. And if you have a building stretching the two, if it doesn't have enough of a tie capacity, you can get big cracks opening up, which translate up to the building. So in the context, this is a fairly basic section. If we took a cut through the auditorium structure up here, and then we have the Avon River coming down the bottom here, and so on the section here we've got the Avon River. We have the big auditorium open space, the galleries up top, and we've got these entry promenade structures on either side. So during the earthquakes, we've got and afterwards we've got the liquefaction, and then we ended up with a building that displaced or took up this new displaced shape. So the most significant things that happened were these outer columns of the auditorium space were quite heavily loaded relative to the inner ones, so they sunk down through into the soil a lot more than the outer ones. And the 100mm slab on grade within the town hall was both pushed up by that excess pore water pressure from liquefaction, but also just didn't have as heavily loaded. So we got this really hogging action over the centre part of the town hall. What was a crazy thing, whenever you went into the town hall to do any work before we fixed it up, we had these stairs that went down and onto this floor. And when you walked down those stairs, it was the oddest feeling, because you felt like you were walking up but downstairs. And pretty much everyone who went in there commented on it as they went in. So what did that translate to in terms of the structural damage? So where these beams and columns had to take up this new displaced shape, we got this cracking occurring all around around these promenade beams at the beam column interface. And we got a lot of this sort of action, which was a lot of the non-structural elements that were connected to the ground, and then the tops of them got basically caught in the middle and squashed by the structure coming down above. So even though this looked quite dramatic, it was a non-structural partition wall that just got caught in the middle. Now, if we look at a different structure on the site, the Limes Room restaurant area, and we took a section looking the other way with the Avon River again down here, and the Avon River shown in the section here. This structure was a bit different, what happened was a bit different. We actually had a slip circle failure on this one, such that a slip circle developed underneath the structure, and its new displaced shape was actually such that it kind of surfed down the hill, such that it was actually tilted up close to the Avon River and tilted down towards the foyer. Now, what that translated to was the roof at the top ended up falling off its support, and these are some temporary frames that we had to put in immediately following that, so that it didn't fall any further. At the floor level, there was actually a seismic gap installed here, or a gap in the structure that widened to about 50 or 100 millimeters following the earthquakes, but it did actually stay. The double T's did actually stay on their support. Now, one of the things that we saw around the foyer and the Limes Room, that was the first floor was supported by pre-stressed precast double T's. We had a bit of a mix of these, what looks like a bit of a spalling failure. Some of it was actually spalling because the walls above put a whole lot of compression load on them. They were quite thin, but also they were actually tied down with a weld plate. So we saw a lot of these, and they needed to be fixed up. So in the aftermath, the geotech engineers and as well as us were all going around assessing what was of interest to us, and this is the plan showing the actual differential settlements arranging around the site. So we actually had 300 millimeters of differential settlement from one side of the auditorium to the other, and then in the foyer a bit of a tilt down again towards the river area. We see this 210 at ground level, but actually it translated to about 300 millimeters in the structure, tilting back towards the foyer, and then over here with the James Hay Theatre, again an overall movement of 100 millimeters, 150 millimeters down towards the river. And then what's a bit hard to see, but these were some cracks that Tonkin and Taylor, the geotech engineers, went in and measured, which was the translation of that lateral spreading into surface cracking. And then a lot of this hashing is actually all the sand boils all around the structure from the liquefaction. Now, one of the most damaged elements in the structure was there was a service tunnel that ran beneath the ground floor it went all the way from the kitchen block all the way down through the Limes Room. It went over across to the James Hay Theatre and all the way around the auditorium. And because it linked all the different structures as all that settlement was going on, we saw a lot of this cracking as the structure took up its new displaced shape. Now, this is a crack measure that you're usually measuring something, point something of a millimeter, but you can see in there, I think that's about 11 millimeter crack, which is more like a ruler rather than a crack gauge to see what's going on there. What happened due to this was the basement tunnels filled up with water, so there was about a metre of water in there after the earthquake, as the waterproofing just couldn't deal with those displacements, and a whole lot of cracking. And what was really interesting was whenever there was an interface of a basement wall, which was relatively lightly reinforced with a big structural column or wall within the structure, the damage really concentrated itself there as the big heavy structure, strong structure, didn't want to accommodate any of that displacement, and the basement wall had to take all of it. Now, some other areas of the building, it was kind of an interesting forensics exercise, really, in trying to work out what had actually gone on during the earthquake and what we now had. So we had things like in the Limes Room at the interface of the kitchen, where we had these overhanging walls, And that corner there used to be in that corner there with the parquet floor. So we knew that there was an overall translation, and given the amount of damage around this area, it definitely had moved back and forth during the earthquakes. And then if we take another example, at the back of the James Hay Theatre, there was a big long block wall that was about 19 metres across and about 20 metres tall, that didn't have a whole lot of support, so it was very flexible. And what happened there was just a whole lot of, because it was so flexible, shaking back and forth. We had this skylight, which you can see in the section here. A lot of that glass smashed and got quite badly damaged. And what all this forensics meant was actually it showed us a few of the vulnerabilities of the structure, such that when actually we went to the strengthening portion of the project, this wall was one of the ones that got quite a lot of strength added to it, or stiffness, in the overall strengthening scheme. Now, one of the exercises that we did in about 2013, I think, was to map all the damage around the structure so that we could provide the client with a bit more certainty or around the crack or the repairs that were going to be required. So we had a team of 2 that went round and mapped all the cracks around the structure where we could gain access, and then we put that into a schedule so that with what the repair strategy was. So a lot of those cracks got injected with epoxy, and then the architects insisted, and it looked quite good, and then those cracks then got painted to look like concrete. So when you had all the structure on display, once they'd been repaired, you actually couldn't tell afterwards. So this structure, prior to the earthquakes, was a locally listed heritage building. It's now nationally listed as a Category 1 building, so part of our heritage and has the protections associated with that. But it would be hard to say that anything that we didn't have heritage or maintenance of the building in mind with what we were doing with the strategies associated with the structure. Limes Room is quite a good example where, with that overall tilt that was in the structure, it was quite obvious when you walked into that building that it was going to need to be fixed up. So that when the decision was made to re-level it, we then started looking at and we were looking at what we needed to do with the structure. A few things started to line up, so we ended up having to re-level the floor. And then when we were looking at the strength of the building, we also worked out that we needed to reconstruct some concrete columns. But probably most notably, one of the big additions that it's fairly obvious that we've done with this building is the new buckling restraint braces to support it in the north-south direction. And that was a direct result of just looking at the overall strength in that direction, and the minor axis bending in those columns was just not enough to support it. But we have some really unique and iconic pieces within the Christchurch Town Hall, which had to be maintained or incorporated in. This stalactite ceiling is one of the ones in the foyer, which was actually taken down, taken off site, and actually so that we could do the work above, and then reinstalled afterwards and brought back to its former glory. The image on the right is some fairly subtle, I think, structural steel that was installed into the conference room above the foyer, where most of the action's happening behind this timber ceiling, where there's a roof diaphragm and cross-brace roof diaphragm, and these are really all you see is these struts bringing the forces back down to the concrete wall. So overall, you're still maintaining the overall look of that, and it's hard to see some of what we did. Now a shot of this is in the Limes Room looking out towards the river. You've got this hugely complex roof truss that's going on in both directions. Now when we actually analysed this roof truss, we found that it was mostly good. There was just a little bit of a connection issue down onto these hammerhead columns that we had to deal with. So when we went to address that, we worked with the architects and the heritage advisors to basically put these quite subtle elements which kind of meld into the rest of what that architecture is doing in that space. So the analysis techniques and the design solutions. So we were, with this building, as I said, we were always keen to minimise whatever we needed to do. But basically our overall brief was, can you please repair this building, bring it back to its former glory as it was before the earthquakes, and please strengthen it up to 100% of the new building standard for the earthquake loading. So a bit of a, in some ways, a basic statement, in some other ways, actually a whole lot of work that we needed to work through. So one of the first things that was done was to create some analysis models of all the different structures. So what you see here is some of the visuals from our nonlinear time history analysis model. So the decision was made to use nonlinear time history, which enabled us to deal with all the non-compliant detailing in the building. So it was detailed or designed in details in the 60s and 70s, and obviously modern codes have a lot more stirrups and a lot more different structural elements. So we were able to create these models and use ASC 41, which is a United States standard, to not only model the stiffness of these elements, but also the strength and the ductility, essentially, and then run scaled earthquakes through those structures, such that we could assess what their overall strength was. And so what you get out of that initial analysis process was you start to see where the deficiencies were. So there were some deficiencies in the promenade beams, which I'll cover a bit later. In the context of, this is the James Hay Theatre model, you can see some of the green elements are showing elements that are actually yielding, but actually well within their life safety elements. So to show a bit of a video of what that kind of looks like, this is a video of the limestone. So putting the gravity loads on, what we're able to do is, once we found that it was needing a bit more strength in the north-south direction, we're able to insert these buckling restraint braces with their appropriate properties and actually run the model and test some of those concepts really, really easily, because we essentially just plugged in the new elements and ran those models to check that we were getting the performance that we were expecting, and nothing unusual was happening, basically making sure we weren't making anything worse. And then the big exercise on this project was actually a whole lot of communication with people. So there was a lot of interest, obviously, it being as notable local structure. So everyone was very keen to understand what it was that we were going to do to strengthen these buildings. Now you can see in blue the big overall strategy, which I'll touch on a bit further on in this presentation, is the raft. But actually you can see with the coloured elements, for a relatively big structure, there wasn't too much intervention that we were going to need to do. But these 3D models that we created in Revit were hugely valuable in being able to communicate to the stakeholders, the heritage advisors, the councillors, the mayor, exactly what we were trying to do, and just how extensive that was. So I can't talk about this building without talking about the ground. As was noted, there was a huge amount of work that was done between us and the geotech consultants to understand how we were going to interact and how that part of the solution was going to work. So Tonkin and Taylor, the geotech engineers, they spent a lot of time working through, I think it was well over 30 different options for what they could do on the ground. We narrowed those down to basically two, which was using piles to support the structure, tying those through with ground beams, or a jet grout lattice with a raft. Now what the piles would have given us was a lot more vertical stiffness or vertical support, but we had issues with translation, or we would still get the building moving towards the river quite a bit in future events. Whereas with the jet grout, with the raft solution, we would get a bit more vertical movement, but that was an overall block sort of translating rather than localized things. So what does that look like in very basic terms? So there was a gravel layer beneath the building about 8 meters down. So putting some jet grout piles down into that, and then building in overall raft, which tied the whole building together and distributed those loads from the building into that jet grout solution. Now, hopefully this video works. That there's a so for those of you who haven't done jet grouting before, there's a bit of an animation here showing how it kind of works. So you ended up with a rig, you poke a hole through whatever you need to, and then what you're doing is you're putting the nozzle down, and as you're lifting it out, you're shooting air, water, and cement out into the soil matrix. And so there's a mix of all of those, and as you lift it out, you're obviously creating this column from the bearing layer that you're after back up into the structure, and you can interlock these piles so that they can give you the performance that you're after. So the next wee problem was, okay, we've got this really big rig, how do we fit that? How does that work with an overall building? Fortunately, Callers and Brian Perry Civil, who came on board, they had these really clever, very short little rigs that were less than 2 meters tall, I think, which would get into some really tight spots within the Christchurch Town Hall. So what does that kind of look like? The geotechs worked away and came up with these magic numbers of replacement ratio of 30%. So what that meant was that 30% of the overall soil underneath the town hall would be replaced with jet grout, and that left 70% approximately. And what the idea behind the jet grouting is, you reduce the shearing actions because you're able to transfer load through these elements. The soil particles within these boxes end up being confined, so they can't liquefy. And obviously for us, it was being able to take the loads from the structure through these elements down onto the gravel layer. So we got some really good bearing there. And what does that look like over the town hall complex? We had over 1,000 of those columns, all interlinked in this sort of structure. Now the main points of this was to get, or part of the performance specification was to make sure that those jet grout piles were underneath the main lower depth parts of the structure. So there was a whole lot of walls around the outside, and so all of those piles went underneath those, and then basically creating cells so that we could get that confinement. And then if we take it into the auditorium and think about how we were going to do that during construction, what we ended up having to do was, if we were doing a pile here on day one, we couldn't do the one next door to it on day two. We ended up having to do a bit of a checker pattern where we'd do a pile here and then second pile would be over here, because essentially we were liquefying the soil again temporarily while the cement and the soil hardened and became an overall pile. And then a section through, just showing we ended up creating these 200 diameter holes through the structure to get down to this layer, pull the nozzle out, and basically create these jet grout columns. One of the challenges we had was that we knew that we could get jet grout equipment into New Zealand, but all the different contractors have different ways of doing it. So us as the structural engineer, we had responsibilities for the raft slab and making sure that the building could accommodate whatever came in the future. Then we had Tompkins and Taylor over here saying, all right, we think we can achieve that with a performance specification, but how do we don't know who the contractor is going to be. How do we tender this and make sure that the solution that we get is something that we can all agree on? So the way that we did that was a whole lot of overlap of modelling and analysis, essentially. So what you see here is a bit of a representation of what the non-linear time history approximated what was going on with the raft. We then had our raft solution, which we had lower bound and upper bound stiffnesses of what the performance was likely to be. And then on the geotech side, they went in and modelled the raft, and we told them what the loads were. So they had their Plexus models representing what was going on with the soil, with an overlap of what was going on with the structure. And then these two things are essentially us trying to bound what we might get. So the top one being achieving that replacement ratio with really big jet grout columns, but quite far apart from each other. What does that mean compared to having lots of little columns, essentially meeting the brief but doing it in quite a different way? Now back to the structure. One of the really interesting things I think during design and analysis was how we solved these problems with some promenade beams. So what we had happening here was the nonlinear time history model was showing us that we had a shear failure through these beams, and these beams, remember, are heritage fabric. So we were trying to keep them in the building if at all possible. So the solution that we came up with was actually a slightly unusual one, but to make the building better or make it perform better, we're actually going to cut some of these flexural bars to reduce the overstrength shears within the centers of these beams. So we worked out exactly what we needed in these flexural joints, and then we removed what we didn't need, and what that was really effective. And these ones were the same ones that were damaged in the earthquake. So it's kind of, we killed two birds with one stone in a way, because we already needed to go and repair these ones anyway. So once we'd done that selective weakening by cutting the bars, we came in and FRP wrapped in that plastic hinge zone, and then the finished product looks like this. Now, one of the wee challenges that we had was, because those beams had gone through a lot of displacement in the through the liquefaction and shaking of the earthquakes, was how much stretch actually has occurred in these bars, and have they actually got enough left over to make it through the future earthquakes. So the team at Home Solutions, they took a bar from another part of the structure and actually stretched it, and while they were stretching it, they tested the hardness, and we know that there's a correlation between hardness and strain. And so what they were able to give us, they broke back the cover concrete, and they basically tapped this bar in a whole lot of 1 centimetre sections all the way along, and what they were able to provide us was the strain that bar had been through, and then we were able to correlate that to what strain capacity was left over, compare that to the demands, and basically show that these bars could go through a future event safely. Now, one of the other more global challenges that we had in the foyer block was we had this big concrete box sitting on these concrete columns, which were strong in one direction but very weak in the north-south direction. So they were basically bending about their minor axis, and they were connected through to the strong axis, these other ones. So what we found pretty early on was that there was really large tension compression forces going through some of these beams. So the way to solve that and sort of disguise it within the structure was actually to clamp this part of the structure back to where the load ultimately really wanted to go. It wanted to go to the stiff columns down here. So let's not fight that. Let's just allow that to happen. So the clever idea that was come up with John, I'm pretty sure, was to go and put these super strands in, unbonded post-tensioning, and essentially clamp that structure back to these columns, which worked really well. So on a future event, you would have to overcome that clamping force before you got tension in those elements. Now, one of the most interesting phases was the overall construction phase of this project. So we knew during design, someone was obviously going to have to build some of these solutions. So we were really keen to help that process and help everyone understand that. So some of the things that worked really well in our favour for this building was the original foundation pads for the building were actually about 3 meters or 2 or 3 meters down below the surface. So a lot of where the raft went in the finished case was a lot higher than that. So we were able to maintain that those gravity load paths, or those load paths, while we mucked around above, either sequencing the raft as it's shown here, so putting the jet grading columns in, building parts of the raft, and then supporting the structure off that piece of raft while we go in and rebuild the columns and rebuild the rafts. And essentially, once you follow that, you can remove the props. Now, the contractor who came on board, Hawkins, they actually employed a different team at Homes to do the temporary works. Now, they had big advantages doing it that way, because that team had access to all our structural models, such that they could shortcut some of the processes for loading and things like that. Now, one of the interesting ones that they came up with at the back of the James Hay Theatre, that wall that needed to be strengthened, we actually needed to replace the wall in here. So they came up with this sequence of building the raft, putting this really large frame in. Remember, this is about 10 metres and this is around about 19, 20 metres across. So you had this really impressive structure in there temporarily just to rebuild the wall there. It looked amazing. Now, while all this was going on, we had multiple aftershocks that came through the building, which made things a bit challenging. And in particular, when the limes room was re-levelled, we had to think about, well, that team had to think about, how do we maintain the lateral support to the structure if one of those events comes through at the wrong time, whilst we go re-level it. So they knew they had to get in there and put jacks in to either lower or build up the building. So they came up with these really cool frames that allowed these beams and column, or the beam and the column, to move up and down. But if an aftershock came through, there was the ability to translate those or support those loads. And we have this great video time lapse of that occurring. So what we have here is this is the limes room structure and just how they're building. You can see the service tunnel running through here. And so we have the raft being built up, and then once they've poured that, they brought in the machine. You can see those temporary frames I had up on screen, and this is the gear to re-level it. If you look carefully, you can see we lifted the structure at this end and actually dropped it at the other end, lowered it down so that the building was effectively level after that. Now, opening day in 2019 was a special event, as it was back in 1972 when the building was first opened. Really significant day for the city, returning the building back to it. So I spent I did a couple of rounds around the building, just really enjoying and looking at all the different things that we'd achieved over that time, and really reflecting on the fact that we had actually done it. So we'd said back in 2011, 2012, when the decisions were being made, and actually being able to say, yes, we did it. We did actually come back and save and repair this building, so that people can enjoy it for generations to come, for another 50 years. What was really cool in the auditorium, they had some music playing, and people was just sitting, just enjoying the space, again, because they hadn't been able to do that for the last 8 or 9 years, since the earthquakes. Thank you very much. Any questions?
Thank you very much, John and Mark. Fascinating run through that. Hopefully you can all still see us all and hear us all. Do type questions into the question box. We've got a few that have come through already that I'm going to try my best to field to John and Mark in some kind of order. And so, John, the first one I'll start with you, which is a question about confidence right at the start of the project. So the question was, I hadn't realised how much you were going to argue the case that this building could be saved when others were maybe doubting it. How confident were you when you were making that case, and what gave you the confidence that the building could be saved?
Oh dear. Yeah, well, it is a confidence game, no doubt about that. It's quite shocking when you're pouring through a city with so many bent and damaged and twisted buildings. And I mean, this one, I think it looked dramatic. 350 millimeters or so of differential settlement and lateral displacement. There was always that doubt, but it was, I think, when you're walking around and realize, look, the shaking didn't cause this damage. It was just the fact that the building had to move to accommodate the shape of the ground underneath it, but it's still in pretty good shape. And so one of the arguments I remember using to the city council was, look, it's actually, if you look at it, it's not badly structural damage. The shaking didn't hurt it. It was, I used the term poor man's base isolation saved it, which the mayor picked up and repeated quite a lot of times afterwards. And so, look, yeah, there's always, I think we can save it. I know there'll be a way, and we had to back ourselves to be able to do so. But it was kind of nice that I think when we sat down with it, we went through, assuming we can get the ground sorted out, and we were heads together with the geotech engineers, we said, yep, if we can do that, then we can arrest it. We can see how we could put a raft slab underneath there, which is most of what we think we need to do. We did some pretty good guesswork actually as to roughly what that was going to be, because we were having to try and estimate at that stage what the cost would be. And so, you know, without any analysis, we think this is what the structure will be. Go for it. And I think we got it pretty much right. So yes, we were cautiously confident, but no, you never know.
Well, it's years of experience, I guess, as well, to back it up. That's fascinating. Next question is a bit more of a technical question, so I'll direct this one at Mark. Mark, did you do anything? You talked about your non-linear time history analysis, and you showed us some impressive models. Did you do anything to sort of validate that against the real-world observed performance that had maybe been observed by those structures through the earthquakes?
We did. John alluded to it before. We don't think the building actually necessarily experienced all the accelerations, but due to the liquefiable soils underneath the building. But we actually did have those scaled records from the 2011 quake. So we did actually run those through the models to see what that would show. What was really interesting, I think, out of that exercise was a lot of the areas that showed deficiencies in the structure showed up in those scaled earthquakes from the actual event to the same ones showed up with the scaled ones to the code, basically. So the deficiencies were sort of binary. They were deficiencies in the structure. But then, yes, we used the nonlinear time history analysis model to kind of look at the global performance, but we also had to do a whole lot of work. Like I showed the Limes room roof structure. There was no way that we were going to model that all in that nonlinear time history. We pulled that out into a separate sort of microstrand type model to analyze that, but used again the accelerations from the nonlinear to understand that.
I think I'd add to that. We had a full peer review, and the peer reviewer was quite insistent that we would be going back and validating those sorts of things. And so, you know, as much as we were able to look at the damage that had occurred and use that as one pointer, we were also spending a fair bit of time, you know, going back to the back of the envelope and just make sure we can make sense of it. So like any analysis, never trust it, always check as much as you can the basics. And it's, you know, obviously you feel happy when it lines up as it did.
Yeah, there's a good parallel there, isn't there? With you showed the hand calcs right in one of your first slides, and you can't be a good hand calculator to check that those models are making some sense, right? Fantastic. So we've had a question about soil improvement and whether you could talk a bit more about. Obviously, you mentioned the jet grouting, but were other forms of soil improvement considered as part of this? What else was an option?
Yeah, they did look at. I don't have the list in front of me, but I remember seeing an Excel spreadsheet with about 30 odd different ones. The ones that we did get challenged on through some of the early peer reviews was whether compaction grouting might work, which I think is a bit cheaper. So that involves obviously putting probes down into the soil and then essentially pumping in grout, but more into the core structure. But we found that we couldn't get it up to the levels that it really needed to be for improving the structure up to what it needed to get to.
I think also a lot of those things were excluded by virtue of the site. We're right next to a river, and so a lot of things we had to be very careful not to let grout in any form escape into the river, which is very hard to prevent. And in fact, we had to go to quite a lot of effort on that at the south end of the Limes room to avoid that. And because it was also on a slope, it was quite complex. So the spreadsheet Mark alluded to, quite a lot of those options didn't go very far before we hit an absolute strikeout.
Yeah, some of those options, like what's done on a lot of sites here in similar-ish circumstances, would be to put gravel columns down. So you put those down, but to get that into the town hall, noting the head clearances that we had, it was quickly struck off the table.
That's interesting. That maybe this leads into the next question as well, because in terms of your solutions and the ideas you came up with, I mean, the question is, were there cost limitations to any of this? And if so, how did you overcome it? I mean, presumably that, you know, some of these solutions are really quite intricate. And I mean, that map you showed of all of the what did you call it, the grouse injection, I mean, it just showed you how vast some of this stuff really was. Could you talk a bit more about that for us?
I might start and let Mark finish. Budget was always an issue. And if I go right back to the effort we made in the first place to even save the building, I was always, I won't say amused, but you know, everyone looked at it and said, this is going to cost a fortune. We can't possibly afford this. It'd be much cheaper to build a new one. And I think, yes, those of us in the know, though, knew perfectly well that you'd build half a new one. You couldn't possibly afford to build anything of the quality and the scale of that with the money they had from the insurance, because it was woefully underinsured. And anyone who thought about it would realise there would also be a lot of cost inflation immediately after the earthquakes, because that's just what happens. And so budget was certainly a consideration. I'm pleased to say that the work we did at the outset, though, we had a pretty good handle on those costs. So it was a known quantity. In case anyone read some of the reports about the cost blowout that happened in the project, I'd point out that, in fact, the cost of the groundworks and the strengthening of the structure all came in within the original budget and contingency that was set right at the outset of the project. And so there was stuff added in later, which is what caused some overruns. But essentially, a pretty good job was done of estimating those costs at the outset and being able to stick within the budget for that work. And it was remarkably well controlled, actually, given the circumstances.
Yeah, and elements such as the jet grout and the raft, they were quantified right early on and compared to the piled solution with the ground beams, and a lot of those solutions came quite close to each other. So then it came down to a bit more of what us as the structural engineers or the geotech engineers needed to achieve performance-wise, and so what the downstream effect would be.
I get one final point in its favour. The alluding back to the type of building it is, that, you know, the brutalist architecture, the modern architecture, everything is on display. All structure is exposed, which it's a two-edged sword, because on the one hand it means that every solution has to be thought through from an architectural perspective as well as a structural perspective. On the other hand, it meant that there weren't so many surprises, because everything was on display from the outset, so we could see what we were dealing with. So the fact that we had such good records and such good knowledge of what the damage was meant that we could be fairly confident of having that covered.
Yeah, like you say, a double-edged sword. At least you could see what you were dealing with. We had a question about temporary works, and I'm going to broaden the question out slightly. So the question was, were the temporary works or the works during construction considered? Did you have to consider earthquake forces during that? So I guess to maybe broaden it slightly further, could you talk about, you know, safety of staff working in a building like this, given that you alluded to aftershocks coming on? So you had temporary works that needed to be designed and built and constructed, inspections that had to happen, all of which had to happen during a period of time where you could have more earthquakes coming through. Can you talk about that?
Yeah, yes, very much, where those temporary works needed to consider lateral loads. So we have that all outlined in our standards, which is really helpful, and they're actually quite large loads. You're sort of talking about 50% of a normal building lateral load, I think, is what it translates to roughly. We did actually have some fairly hefty aftershocks come through, and on those times. So if I remember the Kaikoura earthquake, it was about 1 o'clock in the morning, I think. I remember getting a text message from the project manager saying, "Can you be in tomorrow?" And so I think it was an early start, like it is for us today, where I think we were on site about 6 o'clock in the morning and walked the entire structure, all levels of the structure, to make sure that there wasn't any damage that had got any worse, just to comfort those workers. So nobody came on site during that time. And then if you go all the way back to post-earthquakes, so we had these plans that showed red zones. So some of those areas in the auditorium that were badly damaged, we wrote those off to say, don't go in here. And then when it came to actually demolishing those, they had to do that in a really safe manner, generally from the top, and to stay away from there.
Yeah, that's interesting. Thank you. We had a question from somebody about importance level. So this is a seismic term, so you might want some people maybe are not familiar with seismic engineering, so maybe sort of explain the significance of this. But the question was, what was the importance of the building, and did that have to be improved upon or demonstrated as part of the strengthening? Presumably, as you're strengthening it to 100% of the new building standard, you had to do something about this.
Yeah, so the importance level of this building is importance level 3 here. So it's what that translates to in earthquake terms for ultimate limit state is a 1 in 1,000 year event. And so we knew what that acceleration needed to be. And so all our earthquake scale records that we put through the nonlinear time history were all scaled up to that level of event. It would have always been an IL3 build. Well, in the new terms, it would always be an IL3 building because it contains more than 300 people in a space, which I think is how it's classified in our standards. Whether that was different back in the day.
Yeah,
building, I think.
it was. So just to explain that for the non-seismic people, perhaps. So in the seismic codes, we and other reasons, I'm sure you do it. I can't remember, unfortunately, but I know it's done in most codes around the world. There are different importance levels assigned to buildings according to their occupancy or use. And so from an IL2 building is what we would regard as an ordinary structure, so just a regular office building like we're sitting in. IL3 is, as Mark said, people in crowds or perhaps with valuable contents. IL4 would be things like hospitals, which are required and after an emergency such as an earthquake to be operable. And so this was in that in-between area. Regular buildings are designed for shaking with a return period of 500 years. In the case of this one, as Mark said, 1,000, and in the case of the IL4, 2,500 year return period shaking. So quite a big step. A factor of about 1.3 is what the IL3 would be over IL2 in terms of lateral loads.
Yeah, so it's a significant step up compared to an IL2 building we had to design for. Yeah. Was there this? I mean, this is my pet topic, but I promise somebody else wrote this, not me. Have you done any analysis of the embodied carbon of the project, comparing the restoration works to a replacement building, to work out what kind of carbon you might have saved by reusing what already existed?
No, we haven't. It would be quite an interesting exercise to do with more money.
Yeah, it would. A very interesting exercise to do. I mean, as a matter of principle, I think there's always, the most sustainable building is the one you don't build. The second most sustainable one is probably the one you don't demolish and rebuild. So, on that basis, we feel good about it, but no one has quantified that.
Yeah. No, you're right. You don't need to quantify it to know that you've done the right thing from a carbon point of view. Yeah, it'd be interesting because it's quite a big. I mean, what sort of floor area is the whole building?
Well, I don't have that stat. I should have that stat. I'm not quite sure. I do remember. We kind of alluded to it, but I do remember if we'd rebuilt the structure, it would have been even more than at least 50%, 60% more than what we ended up paying for the end result. From that perspective, obviously that doesn't translate to materials, but
it's significant. I've had a question on sort of dealing with other disciplines. Did the client take the opportunity to modernize the rest of the building beyond just repairing the structure, and how did you deal with other stakeholders who presumably wanted to add their own wish list items to the scope as you went through?
Yes, we did. The most notable example would probably be the James Hay Theatre. So it had a rigging system at the back that was quite old and was known to be quite hard to work with. So that got added to the scope at one point to modernise it so that it became a more modern venue that was a lot easier to manage.
It was a good question. I mean, the interesting thing was that, as I alluded to right at the outset, it was actually the auditorium was internationally well known for its acoustics, and so part of the brief was you must maintain that, and so it was very much a case of the original acoustic engineers, Marshall Day, were there along with Holmes and Warren Amani, all the original designers brought back into it to make sure we did achieve that, which I'm happy to say we did, along with some other improvements, in particular with the James Hay Theatre. The theatre consultant was a bit of a sore point for us because we knew at the outset that we would have troubles with the fly tower because there wasn't enough room for the fly grid. And so they would need to get someone on board and that it could be quite expensive. And lo and behold, that was exactly what happened. So that was one of those blowout things I referred to. I guess the original building had, of course, 1960s or 70s heating, cooling, ventilation. And so that was quite a big effort to try and bring that up to modern standard as well. And so, yes, we had to work quite closely with the mechanical engineer. I think otherwise, the beauty of this sort of thing is that the blueprint was the building itself. It was a heritage building. Everyone wanted nothing to change. And so for the most part, we'd have to say, well, that was what it was. We'll just have to bring it back to that. So we were dealing with archaeologists, I guess, art historians, conservators, all those sorts of people that were looking at things. But for the most part, it wasn't actually that difficult.
And one of the things about the basement being flooded with 1 metre of water that sat in there for a while was a lot of that plant was a write-off, basically. So a lot of that was replaced with new and improved stuff. There were some areas, again, referring to the James Hay Theatre, where I think it was quite cold for performance when they were there. So they did take the opportunity to put a lot better heating and cooling systems. I know in the Limes room structure, all the glazing was taken out and replaced with double glazing because that was all single glazed in the first instance. And then all around the structure within so we had the raft structure, and then there was a polystyrene insulation, and then a wearing slab. In that wearing slab, we had underfloor heating as well, so that improved a lot of the efficiencies associated with that weren't in the original structure. So there were improvements made, but yeah, front of mind, I guess, was that when people walked into that structure, we wanted it to look and feel the same way. So a lot of the improvements that you see had to be carefully considered so that we maintain that character, which was imperative.
Yeah, people just wanted their building back, I guess.
Yep.
We've had a few quite sort of specific questions, so we're going to test your memory of numbers. So I'll give you two in one go. So what percentage of the original structural elements did you manage to save were retained? And was anything left out of tolerance by the time you'd finished? So were there things which would be out, beyond typical current allowances for verticality, straightness, linearity, things like
that? I'm trying to remember what the first one was, but I'll take the second one. Yes, there is things that are out of tolerance. So those promenade beams in particular, it's quite hard to tell unless you're in the know a little bit. When you're walking around those promenades, it is a bit tilted, and that's been left, which wouldn't meet today's standard. But items like the Limes room, it was too obvious. We really had to re-level that to fix it.
Yeah, there's an interesting part of the story there, I guess, because going right back to those "can we save it" days and that earlier question, I guess that's one piece of detail which I might have forgotten. One of the first arguments against repairing the building was that it would be too expensive to re-level, which is when we sat down with the architect and somewhere between us said, well, what if we didn't re-level it? What if we left it as it is? And so it's not immediately apparent, but if you're walking around the upper promenade, there is in fact close to 300 millimetres, I think. Close to 300 millimetres of crossfall in the building, but you can't detect it because there are no straight lines to compare it to. And so the fact that the auditorium is still a bit warped and twisted, no one actually notices it. And because we put the ground floor slab back in over the top of the rafter level, it would take someone with some measuring instruments to go around and realise what the extent of that is. So we very deliberately said, look, we can save an awful lot of money by not trying to re-level it, which would be probably practically impossible. And we're better to throw that money into the other improvements, and we can make this, no one will be able to detect that. It will still be the same old town hall, which turns out to be the case.
Yeah, it's very pragmatic.
Yeah, so that first question, if I remember it rightly, the percentage of elements that were left in place, or I don't know the percentage, but I'll say to put the raft in, we had to remove all that 100 millimetre ground floor slab and those basement tunnels, so they were quite badly damaged, and we kind of needed to get in there to build the raft, have that continuously around the structure. So as John said, that was a really good opportunity, because a lot of that, we could then kind of hide, if you like, the warping, or from one side of the structure. I do remember we basically took 25 mils out each door threshold, such that over time, if you walked around there, you would never detect that you were going downwards, but we were able to subtly get there. It did cause us to have to deal with some of the thresholds. So some of those door thresholds had to be lifted, so that you could still get through with the right head heights. So that was a huge advantage to the overall structural solution of that raft, was we're able to fix that ground floor. But I'd say pretty well, if you took a slice through the building just above ground level, the vast majority of that structure was retained and repaired. So it's really just a lot of the stuff below that we really had to deal with.
Yeah, I mean, it would be 90% probably, with just a few columns had to be rebuilt.
That's amazing. It's really, it's really amazing. I had a question on monitoring equipment. Have you installed any strain gauges or other monitoring equipment to allow you to assess the performance of the remediated structure, including in future seismic events? I don't know if you've had any significant earthquakes down there since your works were finished, but so it'd be interesting to know how the building performed.
No, we don't have them in this particular structure. It was looked at one stage, but we don't have any particular strain gauges or anything like that or have accelerometers. We do in other places around the city, but not this particular structure.
Again, this comes back to the nature of the building. By virtue of being all exposed structure, there's actually relatively few places to hide things. On the other hand, we'd say it's got a whole bunch of strain gauges around the outside of the auditorium in the form of those promenade beams. So because of the modelling we've done, we know exactly what movements we're looking for in the future. So we certainly can do that. But no, unfortunately, we don't have full instrumentation, which would be nice to have in a lot of places.
Yeah, fantastic. Okay, we've got one final question, and I think we're going to draw to a close. And it's a really quick one. We've had a few people ask what time you two had to get up this morning to be able to present at this time.
3:30 for me.
3:45 for me. Yeah, it's not normally an hour I would see on my clock.
No, it's certainly not AM anyway. Well, thank you very much for getting up at such a horrible time in the morning to come speak to us. The presentation, to me, what really came through was what a sort of, painstaking and thorough process went through the whole project, right from the inspections when you seem to map every crack in the building through the analysis with your non-linear time history to justify this thing to modern codes, and then all the different sort of approaches to repair and strengthening that had to take place in so many different aspects of the building. So a real sort of Swiss watch of a project, but an amazing end result. And to hear that you saved 90% of the existing structure, I think that alone is a really significant achievement. So thank you both for your time. Thank you to all of those of you who have joined us for this evening's talk or this morning's talk, depending on where you are. And hopefully we'll see you all again soon at one of our next events. Thank you.
Thank you.
Thank you.